Assalamu alaikum everyone. My name is Tarek Eissa, and today's seminar topic will be about my paper published in SMiLE conference in the last February, a reproducible simulation workflow for either inspired hybrid wheelchair using URDF and PyBullet simulator. Okay. This work I equally contribute with Mark and Dr. Ammar Alzaydi as part of a project, course project for advanced mechatronics. Okay. So this will be the curriculum for today for motivation design, URDF, results, contribution, references. So let's begin by motivation. So according to World Health Organization, WHO, by the beginning of 2024, there was about 0.1 of the whole population, people, that's equivalent to plus 80 million people around the world, need or require wheelchair for their disability in walking. Okay, so since then there are a lot of contributions in this field about healthcare and the mobility. So, for example, there are many solutions concerning about not only moving the wheelchair on a flat surface, but also help that disabled human to reach some shelves, maybe in library, maybe in pharmacy. Also, climbing stairs, going upstairs or downstairs. Going in dangerous areas like rocky land or deep snow or deep sand, something like this. So whether there are a lot of solutions that actually working good, but they should follow the Eissa standards. Okay, but there are some solutions that follow Eissa standards, but also they are not providing comfort to the disabled human. So we are concerning about this, giving the comfort to the human, and also achieving all the missions. Like me as a straight human, I can go with wherever I want. So sand, snow, anything, I can handle that. But as a disabled human, he cannot do that. He needs some help from another human. So they are some of the prior solutions. For example, this are concerning of walking on a flat surface, and also they have a built mechanism for going upstairs or downstairs. Only this. They cannot go in sand or snow. So my inspiration, or our inspiration, that was coming from this video. This video belongs to Hyundai Elevate. This is a robot can navigate wherever it wants. Actually, it's a rescuing robot. So let's see. There are sounds. So the sound was really good, but actually this robot has over 24 DOFs. 4 legs. Each leg has 6 degrees of freedom. So and the robot itself can handle the roll and pitch compensation, so it can stabilize wherever the surface is. So it's like mimicking the human legs, because I think we have 6 degrees of freedom, or maybe more, because we have fingers. It can also fold, so it can be like crocodile, and also it can go like giraffe, so it can be extended. It has module here, the structure that has enough space for battery to working while it's unplugged, so it can go in some rough surface like this. It can also crawl. This crawling can help in rocky land, and can also help in the snowy environment. So it can push the snow back like this. So as I said, it can work as a rescuing robot. So if there are some confined spaces, or some spaces in a mountain, some narrow areas, they can go and rescue some humans there. This is Elevate. I don't know if they are thriving right now or not, but we can extend that work. So our design That was it. The same wheelchair, the same mechanism, but in the field of healthcare. So we are providing the same contribution, but in this specific application. So in our design, we have this. This is the chair itself and the foot mat for the human to rest his feet. The structure base, this structure base is connecting the legs with the chair itself. Also, we have two linear actuators, one on the right side and one in the back side. So the one on the right side is responsible for the rolling compensation. So if I'm walking with a wheelchair and there is some curve or something like this, so I have to make my leg like this, so it will be tilted. So the human itself should be straight, not tilted. So this will compensate this angle. But to what extent? To this extent, 16 degrees, almost 16 degrees. And the pitching the same. If I'm climbing stairs, going upstairs, so the human shouldn't be like this. It should be straight like this. So, and also to this extent, 12 degrees. And this is the leg, the same like the Elevate, 60 degrees of freedom. All of them are rotary joints, revolution joints, sorry. Also here, there is a joystick that should be a manual controller from the human, because we aim that the wheelchair will be fully autonomous, but it's according to the target of the human. I should move like this, so the target is this, but the way of going, that will be autonomous. Also, there is a camera on the left side, so the joystick will be on the right side, the camera will be on the left side for visual feedback. That will help a lot in the processing itself and the processing the environments. So if the human want to go forward, but that forward there are some stairs in the forward direction. So this camera will understand, with computer vision processing, will understand this is stairs, so they can go upward automatically without assigning anything from the human. And also here in the legs, and after the 50 degree exactly, there is a pressure sensor in order to measure how much pressure is applied from the wheel. Is the wheel in the air or not? Yeah, and this is a thing that we didn't talk about. This is a joint in the middle of the wheelchair itself. This joint is actually a novel joint. It's like ball and blade mechanism that can roll and pitch the wheelchair, but also maintaining this in the middle, like mounting the chair in the middle like this, so it cannot flip. The wheelchair will not flip. Okay, so now we have all the design components. So we have to stick to the ISO standards, just like the commercial prior solutions. So our solution meet the standards very well. The length of it, this dimension is almost 100 centimeter. The width is this dimension is almost 70 centimeter, and the height is almost 110 centimeters. So these are some poses that we tested already. This is PyBullet simulator, and this is our robot in it. So this is some poses like normally walking with the wheelchair. This is normal flat surface. So actually we have these wheels not differential like cars, but also caster wheels. So we can go omnidirectionally like this. This is another pose going in a library mode that can unfold and stand like this. So it will help the human to gain the same length as me right now, not just sitting like this. There's another pose of stepping. Maybe if we are walking in a mud, so we are not walking like this. We should make our feet higher a bit to tackle this environment. Also, there's ascending mode. This ascending stairs. At this moment, we should rotate the wheel, not to be like this, but to be like this, in order to not flip the wheel, not flip the wheelchair backward. So I should go like this. So this is the movement, and this is the reverse one, descending movement. So this is descending. And the last one is crawling movement. This crawling movement is just mimicking some animals that can go in the sand, or maybe crocodile or something like this. Sorry, not sand, but snow. So it can push the snow backward like this. It can go like this. So this is the movement. Then the last thing in the design that we have to select our actuators. So mainly we have 24 actuators, 24 motors. Each leg has 6 motors and 2 linear actuators. So in order to choose these motors, so we made a motor torque sizing. So we have to select some cases. Not the best case, but maybe a regular case and the worst case scenario. So the regular case, that maybe 3 of the wheels are touching, 3 of the legs touching the floor, touching the ground. Okay, and 1 is just flying. So this was the case. This is the tripod stance. The other case, which is the worst case scenario, that was just 1 is touching and the other 3 is flying. So this was the single for the stance. So our wheelchair is 580. Our wheelchair 350 kilograms with the human. The wheelchair with the human, 350 kilograms. So after making all of these calculations, we got that the stall torque should be 580 Newton per meter. Okay, but with a safety factor a bit to be sure, because this will be commercial and this will be for healthcare. So that will be 850 Newton meter for each motor, the stall torque. Then the URDF. The URDF is a Unified Robot Description Format. This is how we define any robot to be put or to be used in any simulator. This URDF is just like a tree for all the components of the robot. So we start this tree by the base structure that's connecting everything together. This is in the middle. This is the core of the wheelchair. So it's connecting all the legs components. Link 1, 2, 3, 4, and after 4 there is a pressure sensor, then 5 and 6 for all the legs. Then what else is connecting to this basic structure? There is a component. This is a novel 2DF joint that's connecting the basic structure itself from the middle with the chair. This one, and then the chair itself, the seat, and on the chair there is a camera, real sense camera, and the joystick, the upper IMU. We put an IMU on the chair itself to get the angle and compare it with the angle of the base structure to compensate it well. So this signal will be sent to the linear actuator. What else we have? We have the linear actuator. So this base is connected to the linear actuator, which is connecting to 2DF connection. So what is this connection? Should be between this actuator and the seat, and the same for the y-axis. One for the pitch, one for the yaw, one for the pitch, one for the roll. So this is also should be connected to the seat. This is the 2DF in the middle, and this was the two joints that connecting to the seat. So how we make that connection? The tree of the URDF should be like open loop. There is no option to close this chain. So in order to close this, we develop just a part of a function inside PyBullet itself called PyBullet P2P constraint. P2P means point to point. So we put 2 points on this, connecting to 2 points on the seat. 2 points on this connection, connecting to the 2 points on the seat. So this is part of our contribution to actually spawn this robot with this hard URDF. You cannot imagine how many lines of this URDF it was, but how to spawn this in the PyBullet simulator itself. So our results were actually testing the main test bench and according to the ISO. So this was the first test for the ISO. That was how if you are moving with a car in a road, okay. So and you want to make a return or go in this go on this exit gate or something. So what is the width of the way? What is the width of the road should be to take this turn? So you have to move to the right a bit and go to take this turn. But actually, in our case, our wheels only directional movement. So we actually need only 100 centimeters versus the benchmark for the ISO was 120 centimeters. So we are hitting this bench. So alhamdulillah, everything here is good. The second test was going in an L shape. To move in this L shape very smooth. So also we need only 100 centimeter versus the 120 for the ISO. Maybe it's stuck a bit, but that's because this was manually operated, not autonomous. The third test, that you imagine that you are standing by the door and someone need to open that door. So the door for sure will hit you. So you have to stand back a bit. So how many distance this will you stand back in order to open the door smoothly without hitting you? So this was the distance 3, the distance from the door until the end of the wheelchair. So this distance was 145 centimeter, and instead the benchmark was 152. So we are below everything. We are following the ISO very well. The fourth test was if you have a road or a corridor and you want to make 180 turn, a 180 degree turn. So we only need 140 centimeter instead 152. So yeah, these were all the results. To sum up everything, this was our contribution. We provide a proof of concept CAD design for this novel idea. We migrate the novelty from the point of navigation and cars and this world to the healthcare world. The other one that we can construct the URDF for this wasn't done before, so we didn't rely on any other paper. We just relied on the papers in explaining the prior solutions, not exactly our solution. We also have an asset now to manipulate that robot in PyBullet simulator. The third thing that we follow the ISO standards very well. This ISO 7176-5 with all the tests needed and all the results fulfilled the experiment. Yeah, and these were our references. And thank you.
Great. Thanks. I have one question. Maybe if you go to slide 29.
29? Okay.
Yeah.
So, okay.
Yeah, for safety, your range is less than because of the size of your design. Yeah.
Yeah.
Okay, I can see, because I thought because you have minimum range, maybe unsafe, but because maybe of the size of your.
Yeah, because there is distance here. It's not here as well, isn't it? Are you asking because there is blank distance?
Yeah, you said Eissa, they ask to have the minimum, this one.
Yeah.
This the minimum distance between the wall and the end of
Yes.
of this frame should be 3 meters.
Yes.
Yeah, 3 meters.
Not 3 meters, but 152. 152 centimeters.
What mean this 3?
No. This 1, 2, 3. This is the
okay.
index.
Okay.
Yeah, this is the index of that. So in all tests we hit a benchmark to the minimum. We hit another minimum. So actually, if this can be commercial.
So you hit the minimum because of this. You have
exactly.
small minimum. يعني the size of the frame is less than
exactly
what they have.
Yeah.
Okay. Good. Any question?
Yes.
This is really.
Okay, it's a very interesting project. I just have a question. Usually those people, like disabled people, don't go to snow or sand, to be honest.
Okay.
They don't, even if they can, and they would try to go there, they're not gonna be comfortable going there and with everything. So I like the idea, it's a good idea, but in reality, will they go? I don't know. I don't think so.
Yeah.
But the thing is, I think if you find any other applications, instead of saying that they would go to the snow or everything, it would be more realistic.
Mm-hmm.
The other thing I wanted to ask you about, I may forget that, but the thing is it do you do it in hardware or it's only in
Yeah, I have already 3D printed the part, but it's in the dorms. I already 3D printed a prototype for it, but it's some
big one or a small one?
No, it's a small, it's like this.
Okay.
Yeah, but actually there are many because the wheelchair itself. Let me show you the components. This chair itself should be fabricated from this, for example, this chair, the base one. This should be steel, for example, in the real application, and the legs itself, the legs part should be steel or aluminum, something like this. Also, this should be like rubber or cloth for giving comfort. But actually, that's 3D printed is full plastic.
Yes.
So we have a lot of supports. So this supports like it's not catchy for the eye. So that's why I didn't bring it.
Can in your design, is this, for example, the wheelchair would be controlled manually using?
Yeah.
Yeah, it's not automated. Like I push the button and it will.
Yeah, I mentioned that point. The manual operation from this joystick is just for the human. If I want to go from this point to this point,
Yeah.
so I will make this movement.
Yeah.
But actually, how I will assign how I will assign a signal for the wheels. Normally, currently now they are moving the wheels themselves like this.
Yeah.
Okay,
But there is
but this
another type that it's only using the button.
exactly. And another thing, if there is some stairs in front of me and I want to go upstairs,
Yeah.
so I will just as a disabled human I will move this joystick like this, but with a visual feedback from the camera, it will detect there are stairs. So it will choose the mode that we can stepping upward.
Yeah, but
So
the
actually the
stepping-
order the same.
The stepping process will be using manually or
No, not manually. Not manually.
Not
It will be like functions.
Yeah.
This function, if the camera will detect this is stairs, so it will call function number one. Function number one is moving the wheels with this position, with this pose exactly.
Okay.
So
they
the only order,
Yeah.
the only order from the human will be forward. It's like if there's normal
Yeah.
forward, it will go upstairs the same forward from the human. So the human will do just 4 actions: forward, backward,
Yeah,
right,
I
left.
see.
Yeah.
So in case of stair, for example, the user will sit and the mode will be detected.
Exactly.
And it will go. Yeah. Okay.
Yeah.
Great. Yeah. Thank you. Okay.
Question? في سألك هو.
No, no, it's clear, but, so it will be partly autonomous.
Not partially, but there is some level of autonomy. The highest level is L5 autonomy. The L5 autonomy is not even needed the human to move forward or backward. It just has a mission to do with the human on it. So we are not L5, we are L4.
So
L4 is just autonomy with a human action.
So if the human is moving, if it's like using the joystick to move it forward,
Yeah.
and there is a table in front of it,
Yes.
will it the human should using the joystick go around the table or?
No. With a visual feedback from the camera, but this is not done yet. But it's a further extension. With a visual feedback from the camera, we actually put this camera here for that reason, to make computer vision processing, so it can detect this is an obstacle and the desired pose is far behind that obstacle, so it will turn around.
Okay, great, thank you.
Thanks.
No more presentation today, thank you.